going to collect them from you a little bit later on. I'm going to be handing back those tests a little bit later on today so you can see where those marks are coming from. I'm going to fill out the teacher comment part, and then the interim reports will go home. So they'll either go home today if I get a chance to do the teacher comments today, or they'll go home tomorrow and I'll do the teacher comments tonight. So today we're talking about the chain rule, which we use for composite functions. So in other words, when we have f of g of x. Remember when we were talking about these in Math 12? Another way to write f of g of x is f little o g of x. So in other words, f of g of x. Okay? And you saw this, for example, if you had two functions like g of x is x squared and f of x is 3x plus 2, what would f of g of x look like? In other words, we want g of x to be nested inside f of x. Sandrine? Yeah, so because f of x is on the outside, and it's 3x plus 2, but instead of the x, we're going to stick in the g of x, which is the x squared. So we would have 3x squared plus 2. Okay? Now for g of f of x, we do the same thing, only it's the other way around. F of x is going to get stuck into g of x. So what is that going to look like then? Any ideas? Shay, what do you think? Yeah, so g of x is the outside function. It's x squared. We're going to stick f of x in there, and we get 3x plus 2 all squared. So, and then you could multiply that out. So you'd get 9x squared plus 12x plus 4 if you were to expand that. Okay? So the big thing for us with chain rule is recognizing the inside function and the outside function. Now it's easy when we write it like this, but it's not necessarily as easy when you look at it like this. Something like this as a chain rule, that's pretty easy to differentiate. We learned how to do that with the power rule. We wouldn't need anything fancy to deal with that. This one, if it's written in this way, if it's expanded, we don't need anything fancy to differentiate that. We can use the power rule. But if we have it written like this, particularly if it's raised to a power of something like 4 or 5 or 6, where we don't want to expand because that's going to be a lot of effort, the chain rule gives us another technique that we can use. Okay? And so that's what we're looking at today. So what we're going to do to start off with to do chain rule is we're going to use what's called a U substitution. So we're going to identify what the inside function is, and then we're going to call that U. So g of x as an inside function is just going to be represented by one letter variable. And that way we can ignore it for a little bit, and we are going to set y equal to f of u. And we're going to take the derivative of y with respect to u, just using our techniques that we learned last week. And we're also going to take the derivative of g of x. So we're going to have these two derivatives. And what happens when you multiply, we wanted to find dy by dx. And so when we multiply dy by du times du by dx, we get dy by dx, because the du's essentially cancel. It's not the same as a mathematical cancellation, but it does work the same way. So essentially we're going to be taking the derivative of the outside function with respect to u, and then we're going to be taking the derivative of the inside function with respect to x, and we're going to multiply the two together. Okay? And so we're going to do that a few times as a u substitution. And then I'll show you how, for a lot of you, you'll be able to kind of graduate from u substitutions and go right into doing it without the u substitution. We're taking the derivative of the outside function with respect to x, and then we're multiplying by the derivative of the inside function. Okay? So essentially that's what we're doing. And the big thing for you is being able to recognize the inside function and the outside function, which is not that tricky in most cases. Okay? So here's an easier example, example 1. Okay? What is the inside function here? Sherry, what do you think is the inside function here? 3x squared plus 1 is the inside function. Okay, so we're going to let that be u. And I'm going to use a different color. because I can. Okay, so u is going to be 3x squared plus 1. And the derivative of u with respect to x is just 6x. Everybody okay with that? Okay. So now what we're going to do is we're going to substitute u in here. So y is equal to u squared. Everybody okay with that? So instead of being 3x squared plus 1 all squared, I'm substituting the u, which is 3x squared plus 1 right here. And so I have u squared. So the derivative of y with respect to u, I'm just going to do what? Use the power rule, and I will get what, Colin? If this was an x, what would you do? If it was x squared, what would be the derivative?
2x.
Right, but it's a u, so it's 2u. Okay? And that's the derivative with respect to u, but if we want the derivative with respect to x, we now need to multiply by that, du dx. So we took the derivative of this, and that's there, and then we multiply by the derivative of that inside function. Okay? Now we're not entirely done, because our last step is to substitute back in for u. We don't want to have a u left over. So we're going to put this u as 3x squared plus 1 times 6x, and so that simplifies to be 12x times 3x squared plus 1. And if it is easy to expand and simplify, we would expand and simplify. If we had a huge power up here, then we wouldn't want to expand. We would leave it like that. But since we don't have, since it's a power of 1, we can just multiply through, and we get 36x cubed plus 12x. And that's the derivative of 3x squared plus 1 all squared. Now in this particular case, you could check that to see if it's correct. How could you check to see if it's correct? Emily? Yeah, by using the power rule. So what we'd have to do is expand this and then use the power rule and see if what we get. And this is easy to expand because it's just squared. So let's expand it. So we'll do it this other way. I'm going to insert some space here. Again, because I can. Oh, except I hesitated. Don't hesitate. So if we were to look at it and say y equals 3x plus 1 all squared, sorry, it's 3x squared plus 1, I would get 9x to the power of 4 plus 6x squared plus 1. Everybody okay with that? That's what you get when you square a binomial. You square the first term, you square the last term, you multiply these two together and double it. So y prime would be 36x cubed plus 12x, which is exactly what I got here. Okay? Now, which of these methods is easier? First method or second method? Second method, right? So in a case like this, you probably would just want to expand and then use the power rule. But what about in a case like this? Okay? Where now it's cubed, or if it's degree 4 or degree 5, then it's going to be a lot more work to expand. So having another technique at your disposal is where the chain rule is handy. Okay? It can be messy, but it's still handy. What is going to be the inside function here? What do you think we're going to use for an inside function? Dima? So what we want to do is take something out of there, remove something so that it's easily differentiable. But it also has to be something that's easy for us to differentiate. Anybody want to help Dima out? What would you use for a u substitution in this case?
X squared plus 3.
I agree with you, Alex. So if we let u be x squared plus 3, then du dx, or u prime if you like, u prime is equal to 2x. Okay? And so y is equal to 1 over u cubed, or u to the power of what? -3, right. Okay? So that is easy for us to take the derivative of, hopefully. Y prime, how do I take the derivative of u to the minus 3? Sandrine?
-3 u to -4.
Nice. Okay. Now we have to remember, we also have to now multiply by 2x. Okay. And our last step, well, not maybe our last step, but we need to substitute back in there for the u. So we took the u out to make it so it's not very confusing, but now we need to put the u back in. So we're going to have -3 x squared plus 3 to the power of -4 times 2x. The last step would be to simplify this as much as possible. And simplifying usually means we wouldn't want a negative exponent anymore. So the negative exponent is going to get bumped down into the denominator. And up top, we're going to have -6x. Okay.
Shouldn't that be -4?
Yeah, -4. Why did I write 2? Thank you. Power of 4. Okay? Questions about that? Now, once you've done the u substitution several times and you kind of get comfortable with it, you're going to start to see the pattern here. So notice right at this stage here, we could bypass the u substitution altogether if we think about this as x squared plus 3 to the minus 3. Essentially what we're doing is we're taking the derivative of the outside function at the inside function. So the -3 comes down and the exponent decreases by 1 and it becomes -4. So we get that. But the inside function stays the same. Then we multiply by the derivative of the inside function. So you're taking the derivative of the outside function with the inside function staying the same, and then you're multiplying by the derivative of the inside function. Okay, so you could save yourself some steps if, and it depends too on how complicated the whole thing looks. So let's try another one. Questions for me so far though? Questions for me? So I want to try another one, but all my other ones were trig, so I took them out of here because you haven't done trig yet. So let me pick a different one. Oh, and then I got rid of all these. That's pretty easy. Okay. How about this one? Y equals x cubed times 3x minus 1 to the power of 4. Okay. This is not a straight up chain rule, although you will use chain rule in this derivative. Okay? What do you want to do, Kenny? Okay? I mean, clearly you could expand. You'd have to expand the degree 4 polynomial here. It's doable, but it's going to take you some work, okay? Otherwise, you recognize that you have a product of two functions, and one of those functions is the composite function. So you're going to use the product rule and the chain rule in combination here, okay? So with the product rule, if you recall, or look at your sheet, the product rule says take the derivative of one of the functions. So let's take the derivative of the easy one here. Derivative of x cubed is what, John? Derivative of x cubed is 3x squared. And we leave that one the same. So 3x minus 1 to the power of 4. Okay, so that's the easy part of the product rule. Then with the product rule, we leave the x cubed the same. And we need to multiply by the derivative of 3x minus 1 to the power of 4. Okay? So that, yeah?
Couldn't the derivative of 3x minus 1 to the power of 4 be 3 bracket 3x minus 1 to the power of 3?
3 bracket 3x minus 1 to the power of 3. No, it'll be 4.
Yeah, 4.
Yeah. And times 3. Then you have to times 3. Okay, so it's actually 12. All right, so you're right, but let's go through it step by step here. Okay? So to take the derivative of this is a function within a function. We have our inside function, and then we have our outside function. So the chain rule says, take the derivative of the outside function. So just like Alex said, the 4 comes down. I'm going to put the 4 here just to save myself some steps. And then we write 3x minus 1 to the power of 3. So we've taken the derivative of the outside function, evaluated at the inside function. So the inside stays the same. Okay? But don't forget that last step, we also have to multiply by the derivative of the inside. And what's the derivative of 3x minus 1? 3. So I'm going to multiply that by 3. So I get 3x squared onto 3x minus 1 to the power of 4 plus 12x cubed onto 3x minus 1 to the power of 3. Now, sometimes it's nice to try to simplify these a bit. It kind of depends what you're going to do with it, where you're going to go with it. If you're using this for an application problem, it might be nice to have it a little bit simpler form. I look at it, and I can see, obviously, that there are common factors galore. But I am going to attempt to just take out the 3x minus 1 to the power of 3 at this point. So what that does is it leaves me with 3x squared onto 3x minus 1 plus 12x cubed. And then I can probably simplify that. Well, I can simplify that. I'm just not sure how much it's going to simplify, but it looks like it will a bit. So let's try it. So in here, when I multiply, I'm going to have 9x cubed minus 3x squared plus 12x cubed. So I have 3x minus 1 cubed all onto 21x cubed minus 3x squared.
You take 3x cubed out of all that.
I could take 3x squared out of here. Yeah. And I could have done that right off the bat, but I wanted to see what I ended up with. So I have 3x squared, 3x minus 1 cubed, and I have 7x minus 1. Okay, so that is nice in factored form. And when it's in factored form, of course, what does that allow us to find easily? Zeros, right? And so if we were looking for where the tangent was horizontal, we would know at x equals 0, at x equals a third, and x equals 1/7. So it's nice to have it sometimes in factored form. It's not always necessary, but sometimes it's nice. Okay? Questions about that? Okay. Do you think it would be simpler to expand this all out to get us here? It certainly wouldn't get us into factored form, right? If we had it expanded all out, it would give us a long polynomial of degree 6. So it would give us a long degree 6 polynomial, which might be fine, or it might not be fine because we might have to go back and factor it if we were looking for example zeros. So it's kind of nice that it ends up in a factored form for us. Okay. Questions about that? Should we do one more? All right, let me pick another one. That's not trig. We're not doing trig until after the break. And once we do trig, there's a lot more chain rule options. Okay, here's one other example. Let's say that f of u equals u cubed plus 1, and u which is g of x, is root x. I want you to find the value of f of g prime at x equals 1. Find the value of f of g prime at x equals 1. So this is already set up for you as a chain rule with a u substitution. Okay? So in order to figure this out, we need to find two different derivatives. What's the first derivative we want to find? Liam, what do you think? When we were doing the examples before, Sandrine, you're on fire today. Well, we can find that one, but remember to find that, okay, so we can. So f prime of u, what's the derivative there, Sandrine?
3 squared.
Okay, so that's f prime of u. To find f prime of x, I need to take this, substitute in the root x. So that's a nice substitution right there, right? Root x squared, sweet. But I also need to multiply that by what? I need to multiply by the derivative of u. So I got to figure out what that u is. So u prime, u, remember, is x to the power of 1/2. So what's u prime? This tricked you up on some of you on your test on Friday. What's the derivative of that? Yeah, Emily?
1/2 x to the negative 1.
Yeah. So we need to multiply this by this. So we're going to have 3, and root x squared is just x, so I have 3x times 1/2 x to the minus half. So that gives me 3x over 2 root x. Questions about that? Oh, and then I have to figure out what x equals 1. Right. So when I get to this stage here, I mean, I could rationalize the denominator if I wanted to. If I wanted to write this in the most accepted mathematical form, you would multiply top and bottom by root x. And so you'd get 3x root x over 2x. So you'd get 3 root x over 2. Okay? However, that's not necessary because we are going to be substituting in here for x. So when we let x equal 1, we get 3 over 2, which is exactly what we'd get here when we let x equals 1. So at x equals 1, the derivative of f of g is equal to 3 over 2. So what does that tell me? What did I just figure out? The derivative tells you, Emily? Yeah, the slope of the function, f of g of x, when x equals 1 is 3 over 2. That's what we figured out. So the slope of the tangent, and therefore the slope of the function at that point is 3 over 2. Okay, questions for me? So practice some of these from your textbook, please. And if we are talking about